As thank you. Let me just click on got it. Great. So welcome everybody. The topic of tonight's webinar is very much around sort of how to keep the house cool in summer. As many of you will know, we've run a series of webinars over the last I guess best part of 15 months now. We've covered heat pumps, we've covered sort of the whole retrofit process, we've covered solar. This one's going to be more around insulation, which I think is a good thing to add into the mix. For those of you that don't know us, this is a joint presentation from both Petersfield Climate Action Network and Winchester Action on Climate Change. Judging by the names on the list, I think most of you have heard of us, so I'm not going to go into detail about sort of what we do as organizations, but as you know, we're both environmental charities. We're both running projects that are very focused on home energy, and this I think is a good mix to a good thing to add into the mix of things that we've talked about in the past. We have with us tonight Chris Brookman. Chris runs a company called Back to Earth and is our expert speaker tonight. I think actually, without too much further ado, what I'm going to do is hand over to Chris and let you take it from here, Chris, if that's okay.
We'll remember to unmute myself. Excellent. Thank you very much for that, Peter. Right, let me share my screen. Where's it gone? There we go. Okay, hopefully you can see some wood fibre now.
Yes, we can.
Yep. Excellent. Okay. So dot going. So I'm going to talk about natural insulation and summer comfort. I will mainly focus on internal wall insulation when we're talking about it, and mainly because that has the sort of biggest effect on the internal environment. I'll touch a little bit on roof insulation as well, but those are the kind of areas that I'm going to cover. So we do quite a lot with insulation. We sell a lot of insulation, and we primarily work by creating specifications. So when we're looking at specifications for building, insulation being the most voluminous material in most buildings is also one of the most influential components of it as well. It affects obviously the thermal performance of the building, but that has a big effect on the comfort and therefore the enjoyment and the health. So this isn't all about trying to reduce your carbon footprint alone or your energy performance. It also has a big impact on creating a space that you actually want to live in. So the focus purely on reducing heat loss is again should be tempered with the levels of comfort that you're actually going to attain afterwards, and also the health of the building afterwards. Assessing the different properties of insulation and understanding them means that you can specify them in a way that means you can effectively tailor the internal environment to do most of the work for you. So you don't need to have active systems always to keep it warm or cool it. So there's an awful lot you can do just by using the right insulation products in the right place. Okay, so when we're considering insulation, we look at 8 different roles. I'm not going to talk about all of them because we haven't got time, but I'll go through a few of them. But primarily, we're looking at acoustic insulation, which is a really important topic, particularly when you've got multi-house or multi-dwelling buildings and sort of terraces. Fire protection, natural fibers do burn, but because they burn so slowly, they're actually really good in a fire. They actually give you great protection in a fire. We're looking at the health of occupants and installers. We're looking at comfort, and I'll talk more about comfort of the occupants. We're looking at buildability, which is a big one for architects. I don't know if there's any architects on on here tonight. Architects are great at drawing stuff, but not necessarily great at drawing stuff that's completely buildable. We look at durability, so that there's a lot of durability benefits using natural fibers. Sustainability is a pretty big one for natural fiber, and then thermal insulation, which again I'll talk about more. So starting with comfort then, our sense of comfort within a building is derived by the infrared feedback from all the surfaces around us. So when we have buildings that are at an even temperature, at a obviously a comfortable temperature, but all the surfaces are at a similar temperature, that's essentially a space that we would find comfortable. If we have to have large heating systems or large cooling systems, all of those create draft, and they tend to create uncomfortable spaces, even though the air temperature might be what you would decide is suitable. With all these big temperature differences on the surfaces around you, doesn't make for a comfortable environment. Now, lightweight insulation, sort of really high performing insulation, gives you, tends to have really low thermal conductivity, and the sort of expectation is that you would always go for that kind of product, and it will give you the best U value with the thinnest build-up. And I'll talk about this more, but what those products do is they achieve what's called an equilibrium state. So the speed at which heat moves through them attains an equilibrium very, very quickly. When you look at much higher density materials like natural fiber, because they have something called thermal mass, is a sort of colloquial term, they take a lot more energy and a lot longer to change temperature and to reach this equilibrium state. And so they tend to create an internal environment that is much more stable and changes temperature much more slowly. And so again, would tend to be a more comfortable space. Currently, and this was before the pandemic, heat was killing around about 2,000 people a year, and I imagine that's probably up around 3,000 by now. By 2050, I think it was, that was expected to be over 7,000 a year. So it's pretty important that we look at buildings and really assess how we can improve them so they do stay stable in the increasing temperatures that we get each year. Now, wood fiber and natural fibers have something called a very high decrement delay, and that essentially is the time taken from heat hitting the outside of the building to actually start being emitted on the inside face. And because there is such a long time between heat hitting the outside and reaching the inside, again, this is what is keeping the internal environment quite stable. I'm going to talk about summertime comfort as well. Winter is easy. You can stuff your walls full of crisp packets if you want it. That'll keep you warm. There's very little going on in the winter. You don't have big temperature swings, so you can kind of, during the winter you can keep your building warm with just about anything. But as the temperature rises, as I say, lightweight insulations tend to make for a much more uncomfortable environment, and this is where the heavyweight insulations come. So this is where the natural fibers work. Natural fibers, again, particularly wood fiber, they're very, very complex structures. They've got incredible surface chemistry. So in a plant, they're sucking moisture out of the ground without any sort of energy input. The structure inside them has got vast surface areas, and so they can absorb a huge amount of moisture and not change their thermal performance and not rot effectively. So they're incredibly good at buffering moisture in walls, which is great for internal wall insulation. We produce a lot of moisture in our buildings, and so using an insulation product that can buffer that is extremely useful. So this is the temperature profile from a passive house. So it's kind of the top end of the spectrum, but the blue line at the top here is the internal temperature. And the building does have heating. So this is the winter period here. So you can see it stays just above 20 degrees, sort of 20, 21 degrees. But in the summer, and the overnight temperatures are sort of below -5 or so in the middle of the winter. The two summers either side, actually, if the resolution was a bit finer, you'd see temperatures well above 30 in the peaks here. But the internal temperature is peaking out about 23, 24 degrees. So without any cooling input, you're still maintaining quite a comfortable internal environment. And that's really what the wood fiber materials are doing. So moving on to buildability, this is not what you want your builder to be doing. In this country, we have something called the performance gap, and it's a term that we use for the difference between the design performance and the real world performance. And it's largely related to buildability. So air gaps are the absolute enemy of insulation, but you will tend to find a lot of air gaps in well, lots of buildings, but particularly around insulation, partly because there's a lack of understanding that they need to be eliminated, but also partly because it is almost impossible to eliminate them in many cases. So, for example, if you were building an extension on your house, you were using cavity block work, if you put a rigid board in that cavity and you had a 3 mil gap between your inner block work and your insulation board, you can have around about 150% additional heat loss through that wall. The 3 mil air layer warms up and essentially the warm air just disappears out of the top of the wall. If you have a 10 mil gap, which is pretty much the default for construction in this country, because the blocks aren't flat, you've got the mortar in the joint sticks out and pushes the boards away, you know, all these sort of things. If you have a 10 mil gap, you can have 400% more heat loss. So this is where these huge additional heat losses come. So using rigid PIR boards on paper looks great. They've got fantastic thermal performance seemingly, but because they are largely impossible to install in many situations, and they shrink. So again, if you put them in and they shrink, obviously you're opening up air gaps again. They aren't really a particularly suitable insulation for, certainly not for anything in timber frame, and ideally not in cavity work. Pretty much the only place they work is in solid concrete floors. So it's just something to bear in mind there. And again, you wouldn't use wood fibre in that kind of situation either. You would tend to use a flexible fiberglass or mineral, that kind of thing. The passive house that I showed you does have a performance gap, but it's in the opposite direction. So it performs about 75% better than it was calculated to do. And that's partly because it's very simple to build with. The material is suitable for use in sort of moist conditions, as it were, or it deals with moisture very effectively. So you don't need the sort of vapor barriers and those kind of products that you would normally put with something like mineral fiber. Mineral fiber does suffer significantly as soon as it gets any moisture in it. The conductivity increases dramatically, and so because of that, the detailing is very simple. You're allowing the flow of moisture in and out of the boards, but they can cope with it, and they don't. The thermal conductivity doesn't change. The format of the insulations tends to be quite simple and much more solid than sort of comparable synthetic materials too, and so you tend to get a much better result than you would with the synthetic counterpart. Finally, then on to thermal performance, and thermal performance, again, everyone looks at the thermal conductivity of an insulation material and goes, you know, that's the lowest. I'm going to use that. I'm going to get the lowest U value that I can possibly get, and that's going to give me the best result. But I'm going to have to use a bit of an analogy on this one. So that's U values and the thermal conductivity don't take into account time, and they don't take into account the time taken for temperature changes to propagate all the way through a wall. So you have to bear with me on this one. If you imagine you've got a motorbike and you've got an articulated lorry, and you put your little engine in the motorbike and you turn it on and off it goes, and it go from standing to 50 miles an hour in a few seconds. If you put that same little engine, and that engine is a proxy for your heat flow, you put that in an articulated lorry, it will take a long time to reach 50 miles an hour, assuming it ever does. And so if you look at the distance traveled as a proxy for the amount of energy that is going through the wall, you'll find that the lightweight motorbike, even though the top speed, and we're using the top speed as the U value, even though the U value is the same, the top speed is the same, the motorbike has traveled a lot further than the Arctic. And this is what happens with heat. The heat enters the wall using materials like wood fiber changes very, very slowly. And so over a given period of time, the heat transfer through is actually quite low. And this is what we call decrement delay. And so you might have a wall using a very lightweight insulation and a wall using much heavier weight natural fiber insulation. And you'll find that with varying temperatures, you'll get less heat transfer through the wall with the heavyweight insulation on it. And there have been studies done with identical buildings, one using heavyweight, one using lightweight, and the difference actually in heating requirement was about 25% difference. So it really does make quite a big difference to the overall heating and cooling as well. You're gonna have to bear with me again a bit on this one as well. I'm going to go with a bit of a discussion on tables. So when you're looking at insulation, we've got a few insulation products here. You might look at the thermal conductivity, and that's probably as far as you'd go. You probably never look at the density, and I'm pretty sure would never look at the specific heat capacity. But from those three properties, we can calculate something called thermal diffusivity, which is the speed at which heat moves through an insulation material. And again, we're really only talking about summer comfort here. We're not talking about winter time, because the temperature changes are very minimal in the winter. Transferring this thermal diffusivity figure into something that's probably a bit more meaningful. If we have a roof, we've insulated it with different insulation materials. In the middle of summer, the sun comes up, and by say 8 o'clock in the morning, the heat is beginning to heat the surface of the roof, and that heat is going to slowly work its way through the building. If you've insulated your roof with fiberglass, within about 3 hours, 15 minutes, the underside of that roof, you'll find the temperature is beginning to inch up slowly, and that carries on through the day, and you end up with quite a warm building. If you're using PIR board, you know, the foil-faced foam boards, it takes nearly twice as long as the fiberglass, but 6.5 hours. So say it starts warming up by 8 o'clock on the outside, by 2:30, 3 o'clock maybe, the inside is also beginning to warm up. When you're looking at materials like wood fiber, you've got a delay of just short of 16 hours. So by midnight, the heat in theory is beginning to come through. Well, of course, if the sun's gone down by 9, 10 o'clock, actually, and the external environment is cooling, a lot of that heat is actually radiating back out. So over the course of the day, you get almost no heat into the building through the fabric of the building, which actually makes a huge difference to the comfort inside that building. There we go. So in something that's hopefully slightly more tangible, we did a bit of a homemade experiment here. We took a polystyrene box, which is just in the background here, and we took a wood fiber box in the background here, and we put them both outside, and they're the same size, same design, same thickness, same U value. So in theory, should be the same thermal performance. The wood fiber, for some reason, stayed slightly warmer than the polystyrene, but nonetheless, they're sort of 6.5 and 5.5 degrees. And then we brought them back into the room, which was at 20.28 degrees. Put the lids on, temperature sensor in both, so no differences. You know, we didn't leave the lid off of one and close the other one, nothing like that. So they should have been identical. So within half an hour, you can see that the wood fiber has gone up 0.8 degrees, the polystyrene has gone up 8 degrees. So that's a vast difference between the two, considering that the U value is exactly the same. After an hour, the wood fiber has gone up 2 degrees, the polystyrene has gone up 11 degrees. So polystyrene actually is a pretty awful insulation material, even though quite a lot of people cover the outside of their buildings with it. It is not the best at keeping the heat out. So this is just a video just to show how quickly the temperature change. And you'll notice that come the end, after 5 hours, the wood fiber is still 3 degrees cooler than the environment within the building, and the polystyrene is essentially sort of up at the same temperature. So, and this is just material itself. This isn't location. There's no other external factors. It's just the difference in the speed that heat moves through the two products. So again, to try and put that into something that's a little bit more tangible, if you have an internally insulated house, so they've, you know, the internal walls have all been lined with insulation. You've got a lot of glazing towards the south. You've got quite high heat gains particularly in the spring and the autumn, because the sun is quite low and shines straight in through the windows. If you imagine the occupants are kind of typical working family, the kids are at school during the day, the parents are at work, so the house is locked up by 8:30, 9 o'clock in the morning, and it's not until 4 or 5 o'clock in the afternoon that anyone comes back and sort of opens it up again. Now, a lot of heat will accumulate in the building during that time, and so we need to kind of consider where that heat goes. So again, back to our trusty table. Now, I've created this column here which shows the amount of insulation you need to achieve a 0.5 U value. So we're not talking, you know, passive house standard here. We're talking a probably 75% reduction over an existing building, an existing uninsulated building. So it's a significant reduction in heat loss, but certainly, you know, not anything outstanding. Wood fiber, you need 60 mil. You know, polystyrene might need 50 mil, PIR 40 mil. You know, this is what you need to achieve around that sort of 0.5 U value. Now, imagine all of that heat is warmed up the air inside the building, and that wants to go somewhere. That wants to be transferred into something else so the air can cool down. These numbers here represent the amount of heat per square meter that the materials can absorb, and you can see these bottom four here, which are all the synthetic ones, are absorbing pretty minimal amounts of heat. Looking at the wood fiber here, which is the probably next best option, probably the best option rather, you can see that you've got heat heat absorption of anything between sort of 10 and 20 times that of the synthetic material. So during the day, that wood fiber is soaking up heat from the heat of the sun piling in through the windows. So again, looking at that in a graph, you can see that all the natural fiber materials absorb a lot of heat, and synthetic ones tend to absorb very little. And what happens is the occupants will come home. If that building is really hot, they'll obviously open it all up and try and disperse the heat because it's unpleasantly warm to be in. But if you've got a material that's lining the walls that can absorb that heat, the inside of the building stays at a comfortable temperature, and it radiates that heat back towards the interior as well. So you're delaying the point at which you turn the heating on. Spring and autumn, you know, most people are still using their heating into, you know, April and potentially May, depending how cold it is at night. And so you can actually utilize the heat from the sun really effectively and have a massive impact on the amount of heat that you need. There's a product called effusivity as well, which is again one that's on one of the tables there, and it refers to the amount of energy that or the speed at which energy can be transferred from the material back to the internal environment. And again, wood fiber is very good at transferring heat back to the internal environment. So you've got a material which slowly absorbs heat. Once it's in there, it then quite quickly transfers it back as the internal temperature drops. So it's a really, really useful material from that respect. Okay, another scenario then, hopefully, which will expand your understanding a little bit further. Again, we're all looking at internal wall insulation here. We're assuming internal wall insulation on this brick building. This is a fairly standard 9-inch brick wall. Also, the interior of the roof is insulated because, you know, we'll say in this example, it's in a conservation area, and so you can't raise the roof line and all that kind of thing. So, you know, you've got relatively thin walls. They're fairly dark coloured. You haven't got any sort of shading or anything like that. And if we look at the midsummer kind of behavior, so, you know, we've just had temperatures well above 30 degrees every day for a few weeks. The actual peak daytime temperature tends to come at around 4 o'clock. The peak surface temperature on the walls and the roof will be around about 2 when the sun's intensity actually is the highest. And so typically when you've got a brick wall like this, it delays the heat transfer by about 2 hours. It's not really very much, because although it's got a huge amount of thermal mass, it's also very conductive. So it does transfer the heat from the outer surface to the inner surface quite quickly. The roof will have very little heat attenuation. So going back to our trusty table, we've got our thickness of insulation here. So looking then at the time taken for the heat to penetrate the walls, if we insulate our walls with mineral wool, PIR, whatever. So say it's your external peak temperature is around about, its surface temperature on the wall is around about 130, something like that. It takes a couple of hours for that heat to transfer through the brick, so 3:30, and then add on these time delays. So by about 4 o'clock, you've got heat beginning to come through your walls. Now, that's when the air temperature is also at the highest. So it's not like you can open the windows because you're just going to get a load of hot air in from outside as well. So you've got a situation where you've got heat coming in from every angle. And the same with the roof. You know, if you've got rooms in a sort of a mansard or in a dormer kind of situation, the surface temperature of the roof is rising from say 8 o'clock in the morning by using mineral wool or fiberglass. By midday, you've got heat coming in through that roof as well. All of these are kind of conspiring to focus heat within this building, so it gets really very uncomfortably hot inside the building. And again, the peaks are when the external air temperature is peaking as well, so there's no real way of escaping the heat. And this is the kind of scenario that you get where people who are unhealthily, or rather who are unhealthy, do really suffer and potentially do very badly. Looking at materials like wood fiber, then we're looking at this row. So typically through the walls, you've got 2.25 hour time delay. So again, say your peak surface temperature on the outside is 1:30. That travels through 3:30, and then it takes another couple of hours to get through the wood fiber. So by 5:30, 5:45, you've finally got heat coming through, but because the air temperature is beginning to drop away, you do have the opportunity to actually escape that heat by bringing in ever cooling air. Again, on the roof, if you've got a 16-hour time delay, the heat coming through the roof is essentially barely ever reaching there. So again, in a mansard or dormer kind of situation, you don't have heat piling in through the roof. So you do have a sort of a refuge from these really, really high temperatures. Again, you can see here that the times for heat to travel through natural fiber materials are considerably longer than those for synthetic materials. I'm hoping that some of this is going in. So as I said, this is for situations where you've got people's primary residence, particularly would tend to be older people rather than younger, where they were around more during the day, less able to go somewhere away from it to cool down. And having that additional thermal mass and that really long decrement delay keeps this nice stable internal temperature, so you actually can get away from the external peaks. And as I say, it's pushing the peak temperatures later and later in the day so that you can utilize cool air from outside. And all of that reduces the reliance on cooling, so that you don't have to start putting in air conditioning units in buildings, which A, is going to cost a lot, and B, is going to be unsustainable from an energy point of view as well. So I'm just going to have a quick chat about internal wall insulation. I don't know if any of you know how it would generally go together, but typically, say you had a brick building, you would tend to remove the plaster if it's a sort of failing plaster, but you would need a smooth kind of surface. So you might strip the existing plaster off and replaster it with a new plaster. You would then have a wood fiber board, which is directly fixed to the wall. Now we've got two different options here, just to highlight. So you can either have a version which is fixed to the wall, and then you can directly lime plaster it, which works very well in more historic buildings, because you would tend to have other lime plasters in other parts of the building. We also do a version where you can batten off the surface of the wood fiber, insulate between those battens, so you then have a service void to utilize, and then you can use plasterboard over the top. There's a lot of kickback from the misunderstanding of plasterboard. Plasterboard is actually very vapor permeable. It also has a much lower embodied carbon element than things like lime plaster. So we are quite happy to specify its use and try actually to help people understand the differences in all the modern materials that are available, and actually identify the ones which are usable and actually which are useful, because plasterboard can be quite useful, dare I say it, in this context. So just to explain the process then, and explain again why natural fibres are more useful. Wherever you have a temperature gradient, so in this case, you've got a warm interior here and a warm humid interior, and then you've got a heat flow towards the exterior. Wherever heat flows even, moisture also flows. So you've got moisture flowing through the walls of your building, albeit quite slowly. And then when they're going through, say you've got fiberglass or mineral insulation, you've got condensation forming here. Again, with the wood fiber, you still have the same thing going on here. Where the insulation meets the wall, you get condensation. With the wood fiber, you can actually lock that moisture into the board. The fibers themselves have this vast surface area that they can absorb water molecules onto the surface of without changing their thermal performance and without running the risk of decay. Again, mineral fiber, glass fiber are very sensitive to humidity, and their thermal performance drops away massively as soon as they get the tiniest bit of moisture in there. So with those kind of products, even though they are vapor permeable, they kind of can't be used in a vapor permeable capacity, because you actually need to put a vapor barrier in there, normally in here somewhere, to enable them to work correctly. Anyway, so this process occurs over the cooler months, and the moisture is locked into the wood fiber and some into the brickwork, and then as the external environment warms up, you've got warmer, drier air drawing moisture outwards, and again the internal environment would dry towards the inside as well, and the wood fiber board here dries out to its sort of equilibrium summer state, ready to do the whole process again. And this is an annual cycle. It can go over and over and over again, and that's how we design our systems as well, to make sure that they don't accumulate over time. In terms of how that actually looks, so this is a building that was being done up in Somerset. So the walls were leveled out with a lime plaster. These are wood fiber insulation boards which have been fixed back to the walls, and you use these special insulated fixings here, which are thermally broken, so you don't get cold spots appearing on your walls and moldy spots appearing on your walls. And that's all fixed back to the masonry there. And then there's lots of important things, but one of the big things to remember when you're internally insulating is that you do need to go through your floor. So internal insulation is very disruptive, but it is in many ways the best way to insulate, because you can address the airtightness of the building as well as the insulation levels of the building. As I said earlier, when you insulate just externally, it can be a lot more difficult to address the airtightness of the building, although you're still spending a lot of money on putting insulation on the outside. Anyway, so your insulation boards come up through the floor there. And this is a different building admittedly, but just really to show that you can do all the same things that you would. You can have sockets on the walls, you can have lights, you can have picture rails, moldings at the top, skirtings. There's no need to change the appearance of the room as such. Admittedly, the walls come in a bit, but once that's been done, obviously it can go back essentially as it was. I think that's about the end of my bit. Really just to say, we've got a huge amount of resource on our website. And again, it's not all about selling stuff. It's all free to use. It's free to access. It's applicable with anyone's wood fiber insulation. So whether it's bought from us or bought from anyone else, we've got a lot of specification documents and tools on there. There's a lot of installation guidance as well. So even if you want to use the documents with someone else's system, you can feel free to give it to your builder and they can go through it. We've also got a training platform on there. So for anyone who wants to learn more about wood fiber generally, but also things like air tightness and thermal mass and decrement delay and all the things that I've been discussing, it's all free to access on our website. So if you have any questions, please fire away. Oh, no, that's the wrong one. I'm supposed to do that one.
Thanks, Chris. So I had a question as you were going through, actually. So why don't we start with that? And then if anybody wants to raise a question, just maybe raise your hand, or if you want, type the question into the chat. Either way. Your scenario one, which had quite a lot of south-facing glass.
Yeah.
How does that perform in the summer if you've got wood insulation on the inside? I mean, doesn't the wood insulation actually store the heat in that case and sort of keep the room warm?
It does, yeah, no, exactly that. So the wood fibre is a fantastic way of storing the heat. It will then radiate it back outwards as the internal air temperature drops as well. So, you know, for a very short period of time, you know, when the external temperatures are skyrocketing, you could argue that it'd be better to have no insulation on the inside of the walls, and you'd be right, because actually that would keep the internal temperature slightly cooler. For the other 50 weeks of the year, and particularly spring and autumn, it's much better to have that insulation layer, simply because the stone, yes, it does absorb heat, but it also radiates it straight to the outside instead of radiating it back inwards. But like I say, yeah, the wood fibre will store a significant amount of heat, radiate that back inwards, and reduce the time over which you need to put the heating on each evening.
Okay, so great in the winter, maybe not so good for those 2 weeks when the temperature.
Yeah, exactly. Heat wave, in the middle of a heat wave, you would argue that actually having a stone building, an uninsulated stone building, would be much more comfortable. But that, like I say, is the whatever is 1 or 2% of the year, or 4% if you look at it in weeks of the year, that it might be more comfortable. The other 96% would be significantly less comfortable.
Perfect. Okay, great. All right. And then we had a question in the chat from Steve Pullen. And I'll read it. Your table shows that wood fibre is a lot more dense than the other materials. If wood fibre is used for insulation, how does it affect the structure of a house? Do you need stronger fixings, etc.?
That's a good question. Generally not, because yes, it is more dense, but the mass per square meter is still relatively low. So the one that we normally use for internal wall insulation is 160 kilos a cubic meter, which at 100 mil over a square meter would be 16 kilos. Well, hanging 16 kilos off of masonry is nothing. If you were hanging 160 kilos off of the masonry, it'd still be nothing. So if you've got a masonry building, it's insignificant. For most timber buildings, it's insignificant unless you've got incredibly skinny rafters, which are sort of right on the bottom threshold of what they need to be for strength. That's the only time that we would then sort of consider recommending increasing the depth of the rafters. But yeah, 99% of the time, the mass of the insulation is not relevant.
Wonderful, thank you. And then a question from A. Wells. I'm not sure what the A is actually, so apologies for. In my rudimentary understanding, this particular wood fibre method is only really feasible if completely gutting and renovating one's property. I guess that's true for most internal insulation, actually. I guess that just points to how disruptive is this?
Yeah, no, I mean, you're right. It's internal wall insulation is much more disruptive than external. Again, there will be situations where, on balance, it would be better to use external wall insulation. The reason that as I say, I tend to promote it more is it can be done room by room, which you can't do with external wall insulation because you've got to put up scaffolding. It all needs to be done in one go. It's not subject to weather, which is always the reason that external wall insulation fails and causes issues internally. As I say, you know, room by room, quite often you can retain the existing plaster, so you don't need to remove existing plaster. It can go straight over the top. Yeah, and it's essentially DIY-able as well, because the only, and particularly if you use the plasterboarded version, you know, you can DIY 90% of it, and the last final skim can be done by a local plasterer who are generally to a penny. So there's lots of ways of making it much more accessible to more people than external wall insulation would ever be.
Excellent. Wonderful. Thank you. So any other questions for Chris? No.
Did anyone actually understand what I was talking about? Well, hopefully you can spend time going through the tables and understanding it a bit further in your own time.
I think it's actually it's been really interesting. I think we might when we put this on our website, if you don't mind putting,
absolutely, yeah, of course, yeah.
We'll probably actually introduce it in a slightly different way as well, because I think people have a lot of questions around internal insulation, and I think you've done a really good job of actually explaining how that works effectively, just as much in the winter months as in the summer months, actually. So that's great. Peter, a question for you.
I would welcome a copy of the tables, the 2 or 3 important tables. On my version, I don't know about other people, but on my version, I had the rogues gallery of attendees covering the final column.
Okay.
I mean, and beautiful though we all are, it didn't help. So
yeah, that's no problem.
a copy to attendees would be helpful.
Yeah, I'll send a copy to Peter. That's not a problem at all.
Thank you.
Wonderful, thanks.
Can I just ask a really rookie question for somebody that doesn't understand buildings that well? Are there any times that you shouldn't be using this sort of wood fiber insulation?
Oh, that's a good question. Yeah, not so much wood fiber, but there's plenty of times when you shouldn't. Well, there's a few times when you shouldn't use internal wall insulation, and that is when you've got a filled cavity. So filled cavities should not be internally insulated. So in that situation, you've got a cavity which, quite often can allow the transfer of moisture from the outside to the inside. If you then reduce the heat flow into it by insulating it internally, not only do you get more condensation in it, but you also reduce its ability to dry out, and slowly you get this sort of accumulation of moisture in the cavity. If you've got timbers then going into that cavity in terms of joists, they will tend to decay as well. So internal wall insulation is not suitable for filled cavities. You can do it with an empty cavity, but not filled. And wood fiber, any sort of natural fiber, I wouldn't use below ground. So if you've got basements to insulate, that's when you want to be using normally XP, extruded polystyrene is what we would tend to use, or we've got other mineral-based insulations that you can do the same with. But yeah, so above ground is the critical thing there, really.
And that's because below ground, you've not got the natural sort of drying cycle over the year.
You can tank below ground, and so in theory, you should be okay. But I have never come across a tanking system that has lasted more than 10, 15 years. Everything leaks eventually. And if you insulate over the top of it, particularly with wood fiber, you've got no idea what's going on behind, and it could be rotted out, and literally you just have a skin of plaster there, and the rest is decayed. And so, yeah, below ground, I never recommend using it really. Above ground, we do a lot of there's a software called Woofy, which is what's called hygrothermal modeling software, which does an hourly calculation over 10 years. We normally do it 7 to 10 years, showing how moisture and heat move through the wall and how it sort of ebbs and flows and where it accumulates and all that kind of thing. And so we can reasonably accurately assess specific situations and make sure that that doesn't occur above ground, but below ground you can't do that. So yeah.
Great. I'm just reading actually a couple of other questions that have come into the chat. So from Beverly, my friend's house has very thick walls as it's old, and it is really cool in summer, and once warmed up, stays warm in the winter. Is the problem that our walls in newer houses are just too thin?
That's a good question. Yes, the thick walls do eventually warm up. It's the heat needed to maintain the level of warmth that is comfortable is one thing, and also if you, and obviously you kind of need to leave the heating on a lot to maintain that. If you want to reduce your heating input and you know, for example, if you were working every day and you didn't want to leave the heating on whilst you weren't at home, you just heat it in the morning, you heat it in the evening. If you've got these vast walls, they just soak all the heat up. You turn the heating on and it takes so long to warm the room up that it doesn't actually warm up before you either leave or go to bed or whatever. So really massive walls are sort of okay when you've got very high levels of occupancy and the ability to heat nigh on continuously, but when you don't, they're not terribly useful, which is why we would then tend to put even relatively thin layers of insulation on the inside. It just decouples that enormous time lag that is required to heat this vast mass of building when you don't really want to heat it all the time.
Excellent. Wonderful. Thank you very much. Any other questions? Okay, great. All right. Thanks, Chris. I'm going to hand over to Patricia now then, to close us out for the evening.
Thanks very much, Peter. I'll just share my screen again. I know I'm talking to some people who already know this, so apologies if you've heard it before, but for those who haven't heard it before, I'm just going to briefly run through what we have on offer through both PCAN, Petersfield Climate Action Network, and WINAC, Winchester Action on Climate Crisis, about helping homeowners to decide whether or not natural insulation, like the wood fibre Chris has been talking about, is the right thing for their own homes. And this, I just click through here. So the sorts of things that we can help with, and certainly at PCAN, we have some of these things on our website to start off with some simple energy saving tips, hints and tips, small changes that you can all make quite easily, up to more detailed things that you can do. We can also give you some advice on the eligibility for the various grants and subsidies that are around. There are things like the boiler upgrade scheme if you are thinking about installing a heat pump, and we've got some grants through the project as well for a short space of time. But if there is anything specific that you're looking at, you can have a look on our website, and we've got some pages on grants and subsidies there and the finance that's available. And the main piece of work that we spend a lot of time on doing is the whole house retrofit plan. So these are done by independent retrofit coordinators. And it's a plan for your home. So what sort of improvements can you make to your home to make it as energy efficient and as carbon neutral as possible? And the approach taken is that's set out by PAS 2035 regulations. So fabric first, and insulation is obviously a very key part of that. And alongside that insulation is the ventilation strategy for the building. So Chris has mentioned how moisture can move around as well, but you want to make sure it's not getting trapped within the building. So the reports will look at insulation and ventilation and whether or not you need to make any changes to improve the performance of the building. It goes on to look at the potential of your roof line for things like solar panels, so you can generate some electricity. And how do you set your building up so that you can change over to some sort of low carbon heating? And for most people, that is an air source heat pump would be the recommendation. But obviously, it depends very much on your building as to exactly what the right combination is. The plan will look at the various risks associated with doing any of this work, and it'll give you a plan of action as in terms of the steps it's worth taking so that you can have a comfortable home that it's also reducing its energy usage and carbon emissions. So this slide here gives you an indication of the sorts of information that's included in the plan. So this is the before you've done your retrofit, and it'll give you an indication of things like your energy rating and how much the modelling suggests you'll be spending on fuel bills and how much carbon dioxide you are producing for the home. And the graphs give you an indication of the size of each different area, which is the before picture. And then if you complete the retrofit, then there'll be the after. So hopefully you can see some improvements in your energy ratings, reduction in fuel bills, reduction in carbon dioxide. For this particular plan, they've broken down the measures into 3 different phases and suggested a number of improvements to things like the insulation, extraction fans, double glazing windows, going on to phase 2 with the low carbon heating, and for this one, phase 3 is the renewables. But the specific recommendations for your own home would be tailored to your property. So this is just an example of the sorts of things that are included in the plans. So we can offer subsidised home surveys and whole house retrofit plans via the Super Homes project that we're running at PCAN and WINAC. The cost for the survey and the plan is between £250 and £600. Broadly speaking, it's based on the size of your house. Alongside the plan, you also get a year's free membership of the NEF Super Homes network, and NEF create webinars a bit like this with experts coming along to talk, and they have a newsletter as well, and a number of homeowners who are in the process of retrofitting their homes or have already done it, so there's a bit of peer support there as well. You get a Super Homes design assessment, which measures your carbon efficiency of your home on a 5-star rating. And we also, under the project, have access to a retrofit coordinator who's employed by NEF, and she can help with understanding your plans, help you assess quotes, and handhold a little bit if needed to get you going on your retrofit journey. And for a limited period, we have some capital funding to help you implement your retrofit plans. So there's money to help with certain insulation measures and solar panel installations. And if that's something that you're likely to complete on your own home within the next couple of months, then do have a chat with either myself or Leona at WINAC, and we can help you decide whether or not you might be eligible for some of that funding. So I think that was basically all I was going to cover. If you need to get in touch with us, our website details are on that slide, or you can email me at superhomes@petersfieldcan.org. And I will just stop sharing there and see if there are any other questions that have popped up in the meantime. It's all gone deathly quiet.
That's probably a good sign. I think no more questions. That sounds good. So thank you. Yeah, go on, Patricia.
I've just had a question in the chat about the email address, so I'm typing it now.
Okay.
I'll put my email address there. If you happen to live in the Winchester district, then I can pass your details on to Leona. Great. I look forward to speaking to you.
Wonderful. Thank you, everybody. That's it for tonight. Thank you very much for your time. If you've got any further questions, don't hesitate to reach out to us, and we'll do our best to answer them. Thank you very much. Good night.
Thanks a lot.
Thanks.